Today's session is dedicated entirely to examples, so you can see how the Lagrange formalism works in action. The first example I would like to discuss is a mass on a rotating rod. Imagine in 2 dimensions a rigid rod which is rotating around the origin with a constant angular velocity omega. So the angle of the rod with respect to the x-axis is time dependent, and it goes like phi equal to omega t. On this rod there's a mass which can glide without friction along the rod. Effectively, this system has only 1 degree of freedom, because at any given time we know the position of the rod. It's given by phi equal omega t. And given the position of the rod, the position of the mass on this rod can be specified by 1 parameter only, and we can take for this parameter the distance of the mass to the origin, which I would like to call little r. The constraint imposed by the rod is holonomic. It reduces the motion of the mass from 2 dimensions to effectively only 1 dimension, namely along the rod. Note, however, that the holonomic constraint is time dependent, because the rod itself is moving. So we talked about the fact that there's just 1 degree of freedom in this problem, and the difference is to the inclined plane, however, that the constraint, which is holonomic, the body is constrained to move on this rod, which is rotating, but the difference is that this constraint is time dependent, because the rod itself is moving. At a given time t, we know where the rod is, and we can specify the location of the mass on this rod by a single parameter, and that is this little r, which I drew in red. So again, we have just 1 coordinate, the coordinate r, which is related to the Cartesian coordinates x and y by the following transformation law. The Cartesian component x given r, and here we have to know what time it is to make the transformation, because at different times the rod is at a different position. So we have to know it's a transformation that is time dependent, and the Cartesian coordinate x is given by r times the cosine of the inclination angle at that time, and the angle at that time is omega t. The same for the y component. Y as a function of r and t is given by r times the sine of omega t. So here we have a coordinate transformation which is time dependent. And an immediate consequence of this time dependence is that here the Hamilton function is not equal to the mechanical energy. Next, we have to evaluate the Lagrange function. For that we need the kinetic energy and the potential energy. The potential energy, however, is 0. There is no potential in this problem. We only have the kinetic energy, so the Lagrange function is simply given by the kinetic energy. In Cartesian coordinates, this is the usual expression, mass over 2, velocity squared. And now we can use the transformation law to express that in terms of our new coordinate r. When we take the time derivative, then by product rule, we have an r dot in both cases. And we have to take into account the time derivative of the cosine and the sine functions. And this gives us an extra inner derivative omega. And when you work it all out, you find that this becomes, the velocity squared now becomes r dot squared plus omega squared r squared. And this is now the Lagrange function expressed as a function of the new coordinate r and the new velocity r dot. From this Lagrange function, we can obtain the equation of motion. This is simply the Euler-Lagrange equation. This says d over dt partial L with respect to r dot. This is equal to the partial of the Lagrangian with respect to r. Now remember the form of the Lagrange function. R dot featured there as m over 2 r dot squared. When we take the derivative with respect to r dot, then we get mass times r dot. And the time derivative of that is mass times r double dot. On the right-hand side, well, the dependence of the Lagrange function on r was of the form m half omega squared r squared. We take the derivative of that, we get m omega squared r. And then we cancel out the mass, and we find the equation of motion r double dot equals omega squared r. And you immediately recognize on the right-hand side omega squared r, this is nothing but the centrifugal acceleration. In fact, the Lagrangian formalism is also very suited to derive all these fictitious forces. You can do that very easily, just in the same way we recovered the centrifugal acceleration here. Now, the Lagrange function does not depend explicitly on time. The partial derivative of L with respect to time vanishes. This implies, as our general result, that as a consequence, the Hamilton function is constant. That's a conserved quantity. But remember that the Hamilton function here is not equal to the energy. Well, this is not surprising because as the rod is rotating, we are providing energy from the outside to the system. It's not a closed system, it's a driven system, like a driven harmonic oscillator. And there we supply energy from the outside, and so we wouldn't expect the energy of the system to be conserved. Well, if the Hamilton function is not equal to the energy, what is it then? Let's have a look. First of all, let's look at the generalized momentum. The generalized momentum is the partial of L with respect to r dot. Well, we already saw when we considered the Euler-Lagrange equation that this is simply mass times r dot. The Hamilton function is defined as momentum times velocity. So PR PR times R dot minus the Lagrange function. That was the formal definition. This is equal to mass times R dot squared minus the Lagrange function, which in turn is mass over 2 R dot squared plus mass over 2 omega squared R squared. And when we take this together, this is m over 2, and then we get an R dot squared minus omega squared R squared. This is the formula for the Hamilton function. And you see that this cannot be given sort of a ready physical interpretation, but we learned very quickly and very easily that this is a conserved quantity of the system. That followed directly from the fact that the Lagrangian doesn't depend explicitly on time. The next example is a classic machine called the Atwood machine. The design of that machine is as follows. I draw this in 2D. You have two masses, M1 and M2. These two masses are connected by a rope. And this rope goes over that wheel. And both masses feel the gravitational acceleration g. And the masses can be different, they don't have to be equal. And we say that the first mass is at position x1 and the second mass is at position x2. The task is to describe the dynamics of this system. Following our general procedure, the first question to ask is whether or not there are any constraints. Yes, there is, because the two masses are connected by a rope. So if we call the length of the rope L, and sort of we neglect the little contribution that comes at the top from the rope going around the wheel, then we have the constraint that x1 plus x2, this must always be equal to the length of the rope. So x1 and x2 are not independent, but there's actually only one independent coordinate. It's also clear that there is sort of the second dimension that I indicated. The y direction doesn't play any role here. It's a purely one-dimensional problem. And this constraint is holonomic. It reduces the number of degrees of freedom from 2, which you would have without the rope, to only 1 with the rope. One degree of freedom. Knowing this constraint, you look for a suitable coordinate. And you may choose one of the two positions, either x1 or x2, as your only coordinate. Let's say we choose x1 to be our coordinate. So our generalized coordinate q is simply equal to x1. The transformation law is, we want to go back to the original Cartesian coordinates x1 and x2. x1 of q is simply equal to q by definition, and x2 of q is equal to L minus q. With these coordinates, we'd like to find or express the Lagrange function. For this, we need the potential energy and kinetic energy. Let's start with the potential energy. The potential energy in Cartesian coordinates, this is minus it's the gravitational potential, the potential energy in the gravitational field of the first mass, which is minus m1 g x1, and the potential energy of the second mass in the gravitational field, which is minus m2 g x2. We have the minus sign here because, intelligently or not, the x-coordinate is, or the x-axis here is drawn pointing downwards. Therefore, we have a minus sign. If it were pointing upwards, then you would have a plus sign. Now we can express this potential energy in terms of our generalized coordinate q. And we can write that as gravitational acceleration times m2 minus m1, the difference between the two masses, times q. And then we get an extra term which includes the length of the rope, but is not dependent on the position of the masses. So it's, in terms of its impact on the dynamics of the system, it doesn't play a role, it's just an additive constant. So here we have the potential energy expressed as a function of q. Next we look at the kinetic energy. Kinetic energy is the kinetic energy of the first mass, which is m1 half x1 dot squared plus m2 half times the velocity of the second mass squared. And here, when you insert the transformation law, then both x1 dot squared and x2 dot squared simply become q dot squared. Because L, of course, is constant, time derivative vanishes. So we end up with 1 half m1 plus m2 q dot squared. So taken together, we have the Lagrange function as a function of q and q dot. This is equal to 1 half m1 plus m2 q dot squared minus the potential energy, which is g times the difference between the masses, m2 minus m1, times q, plus an additive constant which will not affect the equation of motion. Given this Lagrange function, we can immediately write down the Euler-Lagrange equation. We have the equation of motion. Euler-Lagrange, following the usual recipe, d over dt of dl partial q dot equals partial L partial q. And now let's see what comes out. Partial derivative of the Lagrangian with respect to q dot will give us m1 plus m2 times q dot. And then the time derivative of that gives us m1 plus m2 q double dot. On the right-hand side, the partial derivative with respect to q will give us minus g times m2 minus m1. We can take the minus sign inside the bracket and can write it as instead m1 minus m2 times g. So the equation of motion reads q double dot acceleration is equal to m1 minus m2 divided by m1 plus m2 times g. Let's see in this case what happens with the Hamilton function. The coordinate transformation between Cartesian coordinates and our generalized coordinate q is time independent. Therefore, the Hamilton function in this case does equal the physical energy. So coordinate transformation time independent means Hamilton function is equal the total energy. The Lagrange function does not depend explicitly on time. This is 0, implying the Hamilton function, which is equal to the energy, is conserved, is a constant. Let's see what it is, what this total Hamilton function is. What this Hamilton function is. For this purpose, we need, again, the generalized momentum, P, that's dl over dq dot. And this we had found to be equal m1 plus m2 q dot. But actually, we don't have to go through the general formula P times Q dot minus L. We can make life simpler here because we know that the Hamilton function is the total energy. So we can immediately write the Hamilton function that is kinetic energy plus potential energy. And for both we already had derived formulas. We already know that the kinetic energy is 1/2 m1 plus m2 times q dot squared, and we already know that the potential energy is, well, the expression given in the first line above, but again I would like to take the sign inside the bracket, so I'd like to write this is minus g m1 minus m2 times q, plus an additive constant. The next example becomes a little more tricky. As we move on, we make it more and more interesting. And that is a mass point moving on a cone. The idea is the following. Imagine a cone, and the Cartesian coordinates are chosen in this way. You have x, y, and here you have the z-axis. This cone has a certain opening angle alpha. And there is a mass which is constrained to move on the surface, say the inner surface of this cone. And the mass experiences gravitational acceleration. So you would expect it to move downwards under the influence of gravitational acceleration. But it's not quite as simple as that, as we will see. It's really just a mass point. We neglect sort of the fact that it's, in practice, this will be a ball of finite size and perhaps it will be rolling. So this rolling movement we're not looking at. We imagine this is a mass point and it's gliding without friction on the inside of this cone. The mass point is constrained to move on the surface of that cone. That surface is two-dimensional. So the constraint is a holonomic constraint. Movement is constrained to a two-dimensional submanifold, so the number of degrees of freedom is equal to 2. Then we should choose suitable coordinates to describe the location of that mass point. And I would like to propose 2 coordinates. One is the distance of the mass point from the origin. This is one coordinate. But then we also have to specify an angle. So we take the projection of the mass point down onto the xy plane, and that will be at an angle phi from the x-axis. So these are the 2 coordinates that I would like to propose. The length of this projection here, the blue line, that is r times the sine of the opening angle alpha. Now from this you can deduce, if you take this projection here and then you project it further onto the x and y axes, you recognize the transformation law. X as a function of r and phi. This is r times sine alpha, which is the length of this blue line. And that projected onto the x-axis gives us an additional factor cosine of phi. As for the y-coordinate, the Cartesian y-coordinate, as a function of r and phi, it's r times sine of the opening angle alpha times sine phi, and the z component, the z coordinate, is given by r times the cosine of the opening angle, the cosine of alpha. We have the new coordinates, we have the transformation law, we are ready to evaluate the Lagrange function of the system. We start with the kinetic part. Kinetic energy in Cartesian coordinates is given by mass over 2, velocity squared, and then you use the transformation law to transform that into an expression with r and phi. In terms of the new coordinates, this is mass over 2, and then we have an r dot squared, and we have an r squared phi dot squared sine squared of the opening angle alpha. Next we come to the potential energy in the gravitational field. In Cartesian coordinates, this is very simple. It's mass times gravitational acceleration times the z coordinate, the vertical coordinate. And here you see immediately when we insert the transformation law that this is equal to mgr times the cosine of the opening angle. Together, this gives us the Lagrange function, written as a function of r dot. And now look at the kinetic energy and the potential energy. Nowhere do you see phi. There's only phi dot. So the Lagrange function depends only on phi dot, but not on phi. This is t minus u. Inserting the results from above, we can simply copy. This is the kinetic part minus the potential energy. This is the Lagrange function. And this is the starting point for deriving the equation of motion, for looking for conserved quantities, etc. We're looking for conserved quantities. And as you correctly observed, the first conserved quantities that we immediately recognize is from the fact that phi is cyclic. The Lagrange function does not depend on phi. The associated generalized momentum, which is defined as dl over d phi dot, is conserved, is a constant. Let's evaluate this, this generalized momentum. As you remember, the Lagrange function, the phi dot entered in a term that had the form m half r dot r squared phi dot squared sine squared alpha. Let me show it to you down in the last line. You see in the kinetic term there's the phi dot squared. When you take the partial derivative with respect to phi dot, you find the associated generalized momentum has the form mass times r squared phi dot times sine squared alpha. And this is conserved. You also see here that this generalized momentum, p phi, cannot be identified with the physical momentum. But it has a different physical meaning. It's not a momentum, but what's written here is actually the z component of the angular momentum. So this is, let me call this little l, or little l z, and this is nothing but the z component of angular momentum. Why? Let's quickly check that. How is the angular momentum defined? Angular momentum is defined as position vector product momentum. So in particular, the z component of angular momentum, this is x times the y component of momentum. So here we are talking about physical momentum again, and we are looking at Cartesian coordinates. So x times py minus y px. What was x according to our coordinate transformation? That was r times sine alpha cosine phi. What is the y component of momentum? It's mass times y dot, the y component of velocity. But y dot in turn is according to the coordinate transformation that has two contributions. It's r dot sine alpha sine phi plus r sine alpha, and then the time derivative of sine phi, which is cosine phi times phi dot. And from this we subtract y times px. Y is, according to the coordinate transformation, that's r sine alpha sine phi times the x component of momentum, which is mass times x dot. X dot is r dot sine alpha cosine phi plus r sine alpha, and then we have the time derivative of the cosine phi, which is minus sine phi phi dot. Now these two terms cancel, because when you multiply the bracket, then on the first line you get an expression with cosine phi sine phi and all the rest, and on the lower line you also get cosine phi sine phi and all the rest, but with the minus sign in front. So these two terms cancel. Then look at the remaining terms. They have the same structure. So they have, in both cases, you have r squared sine squared alpha. You have the mass. You have phi dot. And then in the first case, you have cosine squared phi. And in the latter case, on the lower line, you have sine squared phi. You have cosine squared phi plus sine squared phi, and this is equal to 1. So in total, you have, let me write it in the correct order. So you have a mass, you have r squared, you have sine squared alpha, and you have phi dot. And that's it. And that's the expression that we found above for the generalized momentum associated with phi. So this is the conserved quantity. It has the physical meaning of the z component of angular momentum. And that is going to be useful for the solution of the equation of motion. What else could be a conserved quantity? Note that the Lagrange function does not depend explicitly on time. This implies that the Hamilton function is a conserved quantity. So the second observation is dl over dt is 0, and therefore the Hamilton function is conserved. In this case, the Hamilton function equals the total energy because the coordinate transformation is not time dependent. The Hamilton function can simply be expressed as the sum of kinetic energy plus potential energy. For both kinetic and potential energy, we already derived expressions, so we can simply insert them, and we find that H is equal to m half r dot squared plus r squared phi dot squared sine squared alpha. This is the kinetic part, and then we have the potential energy mgr cosine of alpha. Let's call that E for energy, and this is constant. So at this point we have two constants of the motion. We have this L, which is this angular momentum component, and we have the Hamilton function, which is the physical energy. How can we exploit that in our solution of the problem, in our solution of the equation of motion, which we still have to formulate? Let's look again at the formula for the total energy, for the Hamilton function in this case. It depends on r dot, and phi dot. What we can do is we can express the phi dot in terms of the other conserved quantity, in terms of this angular momentum component. Remember, on this page, the formula for this angular momentum component. So we have these two constants of the motion, h and L. What we can do is we can take the second equation and express phi dot in terms of L. We can write phi dot as L over mr squared sine squared alpha, and then insert this result up here in the expression for the Hamilton function. This tells us that the Hamilton function, which is a constant, which is this total energy E, which is conserved, that E is equal to m half r dot squared. And then for the second term, we use the substitution, we express phi dot in terms of L, and this becomes L squared over 2mr squared sine squared alpha. And then we have the potential energy, which is unchanged, mgr times cosine of alpha. So here we have an expression now for the total energy in which we have eliminated the phi dot, and it depends only on the radial coordinate, on r and r dot. The last two terms, well, the first term that's depends on r dot, and the last two terms only depend on r. And let me call this an effective potential which depends on r only. And what we've done here is that we've reduced the problem effectively to a one-dimensional problem. We started out from the holonomic constraints. We had a two-dimensional problem, but then we found there are two conserved quantities, two conservation laws. Exploiting these conservation laws, we could write down an expression for the energy, which now depends on one coordinate only, one of the two, namely r and r dot. We've eliminated the phi completely, and we've effectively turned this into a one-dimensional problem. And there's now only a single coordinate featuring, which is r. Once we are here, we can proceed in the same way that we solved in Newtonian mechanics one-dimensional problems. That was the first category of problems that we started with. We can illustrate this graphically as we did in the Newtonian case. We can draw as a function of r, we can draw this effective potential, U effective of r. You see there are two contributions to this effective potential. One goes like 1 over r squared. The other goes like r. Both are positive. Both are greater than 0, greater or equal to 0. As for small r, the 1 over r squared dominates, and you have a pole at r equal to 0. So for small r, the behavior of this effective potential looks like this. Now for large r, the second term dominates, which is proportional to r. So you have an approximately linear behavior for large r. This is the shape qualitatively of the effective potential. And I should note, this is for the case that L is different from 0. You may have situations, of course, where this angular momentum component, little l, is equal to 0. In that case, the first term is 0, doesn't contribute, and you have a strictly linear dependence of the effective potential on r. But if the angular momentum component is different from 0, then you have the behavior that I sketched here. Now the total energy E is a constant, it's a given, and let's draw it somewhere here. Let's say this is the total energy E, which is a constant of the motion. And you recognize, as we analyze problems in 1D Newtonian mechanics, there's a lower bound, R min, and an upper bound, R max. In between these bounds, the effective potential energy is smaller, less or equal the total energy. Outside these bounds, the effective potential energy is larger. Physically, the particle is constrained to move between these two bounds. So we will have a periodic motion. We will have the body moving between this minimal distance r min from the origin and the maximal distance r max from the origin. So the mass will oscillate between these two bounds, and this means for this motion in the cone that if initially, and that's an important assumption here, if initially the angular momentum component is different from 0, this means that the mass, as it's moving on the inside of the cone, is in fact spiraling, is moving on a spiral. It's spiraling down until it reaches this minimal distance to the origin. And then it will spiral back up. And then it will spiral back down. And will be an oscillating motion. Of course, in the real world, you have friction, and eventually it will die down, and the particle will fall to the ground of the cone. But if you don't have friction, in this idealized case, you will have this periodic spiraling down and spiraling up. And that may be a bit surprising intuitively, because you think, well, there's gravitational force, it pulls the particle down and will somehow end up at the bottom. And that's also what's going to happen if you have no angular momentum. That's what's going to happen. It will just slide down to the bottom of the cone. But if you do have angular momentum, it will spiral up and down. And that's a consequence of angular momentum conservation. I'd like to just start with an example. And this is going to be one of the next homework problems. So I'm not going to solve it for you. I just want to start it and give you a starting point, and the rest will be a homework problem. And it's the double planar pendulum. The setup is the following. I draw this in 2 dimensions, Cartesian coordinates x and y. We have a pendulum a mass m1 appended to a rod of length L1. And then we have a second mass appended to the first mass So we have a generally different mass m2, which is connected, linked to the first mass by another rod of length L2. The masses experience gravitational acceleration, g, and the task is to describe the motion of this double pendulum. How many degrees of freedom do you have in this system? 2, exactly. You have 2 degrees of freedom. And you can describe these degrees of freedom with 2 coordinates, 2 angles, namely the angle phi 1 and the angle phi 2. So you have 2 degrees of freedom, and the coordinates that you choose are the angles phi 1 and phi 2. As always, the starting point will be the transformation rule that transforms Cartesian coordinates to these new generalized coordinates. So we need x1 as a function of our new coordinates phi 1 and phi 2. We need the y component, the y position of the first mass as a function of phi 1 and phi 2. We need the x coordinate of the second mass as a function of phi 1 and phi 2. And we need the y coordinate of the second mass as a function of phi 1 and phi 2. So here, for you, the starting point will be to write down these transformation rules. You note already here that the transformation, the coordinate transformation, is not time dependent, explicitly time dependent. So you already know at this point that as a consequence, the Hamilton function can be identified with the energy. How do you proceed next? Well, you need the Lagrange function, and for that you need the kinetic energy and the potential energy. So you know the kinetic energy in terms of Cartesian coordinates. That's the kinetic energy of the first mass plus the kinetic energy of the second mass and you express that in terms of the new coordinates phi 1 and phi 2. Secondly, you need the potential energy. The potential energy of the first mass in the gravitational field, that's m1 g times the vertical coordinate, which is y. So you have y1 plus m2 g y2. And again, you write this as a function of your new coordinates phi 1 and phi 2. And this gives you then the Lagrange function as a function of phi 1, phi 2, phi 1 dot, phi 2 dot. And you shouldn't despair. This is a little bit tedious, but it's straightforward. And then the last step is the Euler-Lagrange equation. So d over dt, dl over d phi I dot equals dl over d phi I for I equals 1 and 2. No? So you have 2 Euler-Lagrange equations. These are then the equations of motion for the double planar pendulum. Up to that point, you can write this down exactly for arbitrary angles, arbitrary amplitudes of your oscillation. But then if you go about solving these equations of motion, then you should make approximations and limit yourself to small angles. I hope that these examples have helped make this Lagrange formalism a little bit more tangible, a little bit more concrete. You've seen how useful it is, and you will get a problem set where you have a lot of opportunity to practice that for yourself.